Have you ever stopped to watch a kettle boil? It's a simple, everyday act. You fill it with water, flick a switch, and wait. Soon you hear a rumble. Steam begins to pour from the spout. That steam is water, but it's no longer a liquid. It has transformed. It has changed its state into a gas. This is a phase transition, a kind of everyday magic. We see it all around us, in the mundane and the magnificent. From the kitchen counter to the grandest cosmic scales, think about a cold winter's day. You might see your breath misting in the air. Warm, moist air hits the cold and condenses into tiny droplets. That's another phase transition. Or an ice cube melting in your drink. A solid gives way to liquid. It changes its structure and properties. These changes happen constantly. They are governed by two key things, temperature and pressure. On Earth, we live in a narrow, stable range of both. Our atmosphere pushes down with steady pressure. Temperatures follow predictable patterns. At sea level, water freezes at 0 degrees C and boils at 100 degrees C. But what if you change those rules? Remove the pressure of the atmosphere entirely. Expose that ice cube or drop of water to the extreme cold and emptiness of space. The familiar magic becomes far stranger. The rules we know are rewritten. In the vast, silent expanse, changing state becomes a window into fundamental laws. And it holds secrets vital to our future among the stars. Our planet is a beautiful, dynamic place. It is a world of flowing rivers, frozen poles, drifting clouds. All of these features are expressions of matter in its different phases. The water cycle is a grand, planetary-scale demonstration of phase transitions. Water evaporates from the oceans, becoming a gas. It rises, it cools, it condenses into liquid droplets to form clouds. It might then fall as rain, or if it gets cold enough, freeze into solid snowflakes. This constant cycle of transformation makes life on Earth possible. It shapes our landscapes, it dictates our weather. But our world is just one tiny corner of the cosmos. When we look up at the night sky, we are gazing into an immense laboratory. Phase transitions occur there on an unimaginable scale. The birth of stars is one such event. Vast clouds of cold gas and dust spread thinly across light years of space begin to collapse under their own gravity. Pressure and temperature at the core skyrocket. A new state of matter is born. Plasma. Atoms are torn apart. The star ignites in a flash of nuclear fusion. Even the death of stars involves incredible transformations. When a massive star runs out of fuel, it cannot support itself. It collapses catastrophically, then it explodes in a supernova. In that brief, violent moment, new elements are forged. Matter is crushed into exotic states we can barely replicate on Earth, like the ultra-dense material that forms a neutron star. A teaspoon of this material would weigh billions of tons. This is a phase transition on a cosmic, violent scale, seeding the universe with the building blocks of new worlds. From the swirling mists of a nebula to the solid crust of a rocky planet, phase transitions are the engine of cosmic evolution. They're about how the universe builds complexity from simplicity. A diffuse cloud of hydrogen can become a planet, an ocean, perhaps even life. Understanding these processes here on Earth is the first step. But to truly grasp the cosmos, we must venture into an environment with completely different rules. The vacuum of space. So what is it that makes space so different? The answer is, in a word, nothing. Or at least very, very little. The space between the planets and stars is what we call a vacuum. It's not a perfect vacuum, as there are still stray atoms and particles drifting about. But it is emptier than anything we can create in a laboratory on Earth. This profound emptiness has a dramatic effect on matter. Here on Earth, we are constantly being pushed on by the air around us. This atmospheric pressure acts like a lid on a pot, holding things in place and influencing how and when they change state. In the vacuum of space, that lid is removed. There is virtually no external pressure pushing down on a substance. This single fact changes everything. If an astronaut were to release a cup of water outside the International Space Station, it would not simply float there as a placid blob. The lack of pressure would cause it to boil instantly and explosively, even though the temperature is incredibly cold. The water molecules have nothing holding them together, so they fly apart, turning directly into vapor. At the same time, space is a place of extreme temperatures. In the shadow of a spacecraft, temperatures can plummet to hundreds of degrees below zero. In direct sunlight, they can soar to well above the boiling point of water. This creates a bizarre paradox. The boiling water I just mentioned would also be freezing at the same time. As the water boils, the fastest moving, highest energy molecules escape as vapor. This process, known as evaporative cooling, rapidly steals heat from the remaining liquid, causing it to freeze into a cloud of tiny ice crystals. An ice cube left in space wouldn't necessarily melt into a puddle. Instead, it might skip the liquid phase entirely, turning directly from a solid into a gas in a process called sublimation. Metals can behave strangely, and materials we consider stable can degrade in unexpected ways. Space is the ultimate laboratory for testing the limits of matter, forcing us to look beyond our earthbound experience to understand the true universal nature of phase transitions. Building a spacecraft is one of the greatest engineering challenges humanity has ever undertaken. These are not just machines, they are self-contained worlds, designed to protect their delicate human cargo and to shield sensitive electronics from the most hostile environment imaginable. Consider the problem of outgassing. Many Earth materials like plastics, adhesives, and lubricants slowly release trapped gases. On Earth, it's often unnoticeable. In vacuum, the process is dramatically accelerated. The released gases can form a thin film on nearby surfaces like a camera lens or a solar panel. A spacecraft could be blinded or lose its ability to generate power. Engineers select special space-rated materials with extremely low outgassing and often bake parts in a vacuum chamber to force volatile compounds out on the ground. Extreme temperature swings pose another huge design challenge. Cycling between these temperatures creates immense thermal stress. That stress can cause fatigue and cracking over time. Engineers use clever thermal control systems. Reflective multi-layer metallized blankets insulate the spacecraft. Radiators, painted with heat-emitting coatings, dump excess warmth. These systems keep internal temperatures stable, protecting astronauts and equipment. It's a constant battle against extreme physics. For an astronaut living and working in space, the management of liquids and gases is a matter of life and death. The International Space Station is a sealed environment, a tiny bubble of Earth-like atmosphere. Launching all needed water is too heavy, so the station uses a sophisticated water recovery system. It collects moisture from the crew's breath, sweat, and even urine. It purifies water through filters and by distillation. Wastewater is boiled at low pressure into steam, contaminants are left behind, and pure steam is recondensed into liquid water. Controlling the air is equally vital. Life support constantly removes toxic carbon dioxide from the air using special sorbent materials. Those materials are exposed to space vacuum, which forces the trapped CO2 to release, and it is vented overboard. An astronaut's lifeline depends on reliably controlling matter as it cycles between liquid and gas day after day in the unforgiving environment of space. Modern rocketry depends on an extreme form of phase transition, the management of cryogenic fuels like liquid hydrogen and liquid oxygen. These are so cold that they are constantly trying to boil. Managing this boil-off is one of the biggest challenges in rocketry. For future missions to Mars, this constant loss of fuel is a major problem. A spacecraft could lose a significant portion of its propellant, leaving the astronauts stranded. To solve this, engineers are developing new technologies called cryocoolers and zero boil-off tank designs to keep the liquid cold enough that it doesn't boil. Preventing that phase change is absolutely essential for our future as a multiplanetary species. It all comes down to controlling that fundamental transition from a liquid to a gas. As we stand on the precipice of a new era of space exploration, the future lies in learning to use its unique properties to our advantage. Phase transitions will let explorers live off the land on other worlds, in situ resource utilization, or ISRU. Imagine robotic miners on the moon, tents trap vapor from heated regolith. Vapor is channeled to a condenser, a cold surface where it becomes liquid water. Phase transition physics turned into life support. This water is more than a drink. Via electrolysis, an electric current splits H2O into hydrogen and oxygen. Oxygen becomes breathable air. Hydrogen becomes rocket fuel. The void becomes a cosmic petrol station. It's a profound shift. View vacuum and extreme temperatures as tools, not just hazards. Harnessing the void is the next great frontier. Our study of how matter changes state in space does more than just help us build better rockets. It provides us with a powerful lens through which we can understand the universe itself. Consider Jupiter's moon Europa. Beneath that solid crust, tidal forces generate enough heat to maintain vast liquid water oceans. Plumes of water vapor have been seen erupting from Enceladus, sublimating from that subsurface ocean. By studying these plumes, we directly sample a hidden ocean. The formation of planets is a story of phase changes. The phase diagram of water helps dictate a solar system's architecture. Every experiment with sublimating ice is a small step toward deciphering the fundamental rules that govern the entire cosmos. In the end, our fascination with space comes back to a very human question. What is our place in the universe? For all of human history, we have been a species tied to one world. To venture into space is to step away from those foundations and learn to survive where our intuition can be dangerously wrong. Seeing a cloud of ice crystals form from a released drop of water is a lesson in humility. It reminds us our earthly experience is one small part of a much larger reality. This journey changes us. It is a shared quest that unites us and pushes humanity's boundaries. The strange dance of molecules in a vacuum shows the counterintuitive beauty of the cosmos. It inspires us to ask bigger questions and dream of a future beyond a single cradle. We began this journey with a simple observation: a kettle boiling. Yet this humble act of transformation is a gateway to understanding the entire cosmos. The vacuum of space, with its near-total absence of pressure and its wild extremes of temperature, rewrites the rulebook. This shift from curiosity to capability is how humanity always advances. We observe, we understand, and then we harness that understanding to build tools. The story of matter transforming in the void is our story. A curious species learning the rules of the cosmos, one phase transition at a time, taking its first tentative steps toward the stars.